everyone. Previously, people used to detect the different category of the IDJs manually, and detecting the various category of the IDJs manually is extremely painful task. It is a critical problem. Therefore, how can we detect the different category of the IDJs automatically using the help of artificial intelligence? And in today's topic, I am going to explain you how to create a artificial intelligence model to detect the different category of the eye diseases. For instance, for the eye disease can be detected using the AI in three stages. The first stage is the data pre-processing stage. Here we load the different uh, categories of the eye diseases. Then after that we apply the data pre-processing technique, like we read the image, we resize the image into the fixed dimension, for example 128 cross 128 cross 3, where 128 cross 128 represents the height and the width of the image, and 3 represents the channel number. It means if it's 3, then it means it is a RGB image, it is a color image. If the channel number is 1, it means it is a grayscale image. And once the images are loaded and then resized into the fixed dimension, then we normalize the pixel value in the range 0 to 1 by dividing the each pixel intensity of image by 256, because the maximum possible value of the image is 256. That is the pixel intensity value, maximum value. And by normalizing the image, the training of the model becomes smooth. And once this data pre-processing stage finishes, then the next stage is model training. And in this model training, we create a model, machine learning model or AI models. Then after that, we train this model with our pre-processed images. And once this model is trained, then the testing phase begins. In testing phase, we pass the different category of the images of the IDs and validate whether our model is working fine or not. And for this experimental approach, I have downloaded the image of IDJs from these websites. I provide the description link of these datasets in the description part of this video. Here are two category of the dataset are here. They both are the same. And first is the original dataset whose size nearly 1.5 GB. But for the experimental purpose, I am using this augmented datasets. It is a bit larger than compared to the original datasets, and size is nearly 2 GB. I will provide the link of this dataset in the description part. And I will show you the datasets. This is the dataset that I have loaded. I have downloaded. I stored it in my Google Drive, and this dataset contains the samples from the 10 different categories. For example, this is the one category of the eye diseases. This is the second class or the second category of the eye disease. This is the third category of the eye disease. These are different category of the eye diseases that is available in these datasets. For example, disc edema contains total 762 samples, and these are some of the images of this disease, disc edema. These are some of the images of this disease. Next, similarly, this diabetic type of the disease contains 3,315 images are there, and these are some of those samples of these diseases. And this is this type of the samples of this disease which we are going to detect in our models, that is the AI models that we are going to judge. And similarly, the healthy eye images can be seen here. This is the sample of the healthy eyes. There are total altogether 2,415 images are here, and you can see here the sample of the healthy eye looks something like that, something like this it looks. Okay, now let's go to the coding part. I have downloaded these datasets and uploaded in my Google Drive, and you can see here, this is my drive, and my drive search datasets, and I have got so many datasets are there for the experimental purpose, and this is the I datasets. It contains the 10 different category of the IDJs are there. Now, first of all, this is the first part of the code, and firstly, I would like to tell you that I have already executed my code and save it in order to make this video short and simple. The first line of the code is used to mount the Google Drive with your Google Colab so that I can access my datasets, my files that are stored in my Google Drive. Similarly, this code is used to check whether I am using GPU or not. If I am using GPU, it will display that I am using this Tesla T4 GPU, and if my GPU is not running, this will simply print not connected to the GPU. And here this is the first phase, data pre-processing. Then next is the training phase, model building, and next this is the model building where I am designing my model, AI model, and I am training this model in this code. And this is the code, this is the part where I have tested my AI model with the different category of the IDGs sample. Data pre-processing. And this is my actual location of my datasets of the I datasets are stored in this location. I have specified the path here. Next, here in this line of the code, I am reading the total number of the images. For instance, here globe is used for pattern-based file searching, example finding all the images in the subdirectory. And OS library I have imported to provide the functions to interact with the file system, example for joining the paths. Next is the dataset path. I have already specified here this one, dataset dir. Next is the image extension, and I am reading the image of the extension JPG, JPEG, PNG, BMP, and GAIF. I am defining a list of common image formats that I am going to read. This helps in filtering files to include only the valid image types. Okay. Next is image files. I have created an empty list image files that will store and print all the image files that are present in my I datasets. Next, I have used this extend function, and this loop or for loop is used to iterate over the image extensions. That it will iterate over the extension like this JPG, JPEG, PNG, and BMP. This line is used for the looping on the different extension that I have specified. And next part is this one here, reverse equal to true, globe reverse equal to true, and this part of the code is used to searches. This part of the code searches for file matching the pattern in all the subdirectory, and it will return a list of the image paths that matches the given extension. This extension that will match, it will return. And next. This extend function is used to add all the image file paths to the image files list, and similarly this code is used to display the total number of the images that are present in the datasets. Altogether I have 14,000 samples of the different IDJs. And next part of the here, this part represents the data augmentation. It means I am increasing the number of samples in my images in my datasets so that there will be no overfitting problem. Here, first I am importing the data generator, image data generator, from TensorFlow.keras preprocessing.image. And this class is used for the data augmentation specifically, which apply the random transformation to the image to improve the model generalization. And these are some of the techniques that I'm applying for to increase the size of my images. And here rotation range equal to 20 means my image, this code will rotate the image randomly up to plus 20 degree or minus 20 degree. Tilt the image a bit slightly, and next wide shift range, this shift the image horizontally by up to 20% of its width. And due to this moves the image left or right. Similarly, next height shift range 0.2 shift the image vertically by up to 20% of its height. Similarly, shear range 0.2 applies a shearing transformation like slanting the image a bitly. Next is zoom range, and this is used for zooming in or out by up to 20%. Horizontal flip equal to true means it will flip the image horizontally with a 50% chance. And fill mode nearest means it is used specifically for, and it is used for it fills missing pixels after transformation by copying the nearby pixels. And how this code works: every time an image is loaded during the training phase, it will be randomly transformed using these augmentation techniques that I have applied here. And due to this, prevents overfitting by making the model more robust to variation in the datasets. Next, now I'm going to I have applied this data augmentation. I have selected this data augmentation technique. Now I'm going to read the images by applying this data augmentation technique. Firstly, I have imported this image, PILT image, and it is used to open and resize the images. And next I have imported the NumPy, and NumPy helps in storing the image data as arrays and for the smooth training also. Next is OS. Also I have used here OS, and this OS is used for to handle the files and directory operations. I have created here function load images from the folder, and this is used to load different images that are stored in my datasets. Here this line class is equal to sorted, class name is equal to sorted is used to read all the subfolders names. Example, the class name for it means the different category of the IDGs. The class name, these are the class names. Here these are the different category of the IDGs, these are the class names. I am reading this using these codes. Next, for label class name in enumerate, it is used to iterate over each class folder and assign numerical label to each class. Example, for example 0, 1, 2, and print the class name to track the progress. Next here, what is actually happening in this code is it will loop through all the image files in the class folder, opens each image and resize it to 128 cross 128 dimension, convert the image to a NumPy array form for the smooth training, and it also opens the image to images list, and its corresponding class labels to labels list. Next line of code is, and here images np.array labels np.array, it converts the Python list into the NumPy arrays form for the faster processing. Here this line of the code is used to create the empty list for the augmented images and the labels, and it loops through each image and reshape it to the compatible form with the image data generator that I have used for the data augmentation, and apply the data augmentation using datagen.flow, this one, which generates the newly transformed images, and it stops after generating the two augmented images for original. Total three versions for image will be generated. I am applying here double of the data augmentation technique, and here this code is used to save the process data. For example, whatever the images, labels, and class name I've read to my Google Drive, and I'm using numpy.np.shape to store these arrays that I've read, data, images, and labels, and class name in the form of numpy for the faster loading, and this ensures data is persistent even if the notebook restarts. Even if I close my notebooks, my Google Colab, I can still load these data sets that I have already read. No need to read from the beginning. And here this code is used to load the data sets that I have read. It is used to load the images, and this line of the code is used to load the images, labels, and class that I have already read and stored in my Google Drive. And here in this line of the codes, my dataset that I have read and stored in my Google Drive will be loaded. And this line of the codes here, image.shape bracket 0 is used to display the total number of the images of the IDGs. It will display. Similarly, labels.shape will print the number of the images per label. Total number of the label, how much is available, it will read. And similarly, the class underscore names will print the list of all class names. For example, what type of the IDGs are there, it will just display. For example, I have 10 different category of the classes, 10 category of different IDGs, so it will print this classes name here. Here in this code, I am trying to visualize the data set that I have read, and for the visualization purpose, I am using the matplotlib library. I have imported this library in the form of PLT. Now next I am visualizing these data sets. Here in this code, selected images. The selected images here is used to get the total number of the unique classes, and similarly selected images is used to store one representation per image classes. Similarly, labels will be used to store the corresponding class labels. And in this below code, here in this code, my code will be iterated over all the images and the labels of the IDGs. Check if a class label is already seen or not. If not seen, select the first image of that class. Stop when it has collected one image per classes. Here in this line the code, figure size 15:6, it will create a figure with a size of 15, 6 minutes. 15 inch will be the height and 6 will be the width. And column school equals to, this means the line of the code will create the maximum 5 images per row will be displayed. Here the 5 images are being displayed, and it has 15 this length, and 6 of this height is this width. This is the 6th, and this is 15 inch. I am creating this figure of 15,6 size and displaying this my images of the different IDGs. Here in this code, plt.type layout is used to adjust the spacing between the subplots to prevent the overlap between the images, and plt.show is used to display the final complete visualization of this information. And here the different category of the images of different diseases are being shown. For example, this image is of the eye disease disc edema, and this one is the of the disease glaucoma, and this is the healthy eyes. I am just displaying a single image of each different category of the eye disease classes. For example, this image is of musculoskeletal disease. This image is of myopia disease, and this image is of pterygium, and so on. And the next code here, this is also the same code. I am displaying same classes and their respective images in this line of the code. And here in this line of the code, I am generating a pie chart which will show the distribution of the different classes. Here for this I am writing this one code. Here I am generating this pie chart. This shows the distribution of the different category of the eye diseases. For example, out of 100%, myopia is 10.6% of the total images, and this one diabetic diseases has total 23.6% of images out of 100%, and what about healthy images are 17.3% out of the total images. This represents the distributions of the different category of the eye disease sample that I have loaded. Next here, here the same thing I am generating is, but in the form of the bar chart. I am using here bar chart for the generation of this bar. I am displaying the class names. These are the class names, different category of the eye diseases, and I am printing the count. Count means the total number of the images that are present in each sample. For example, this sample has near about 14,000 of total images, and this category of the eye diseases has this 11,000 of the images, and this is the visualization of the different eye diseases in the form of the pie chart. This was in the form of pie chart, and this was in the form of bar chart. And next, this line of the code is used for splitting my training sample, and for splitting my training sample, I am importing the train test split from the sklearn library, and these images are my total training samples, and labels are my its corresponding labels of these images, and I am splitting these images and labels in the ratio of 9:1. It means 90% of the images will be used for the training, and 10% will be used for the testing. And similarly, I am also splitting the labels. 90% will be used for the training, and 10% will be used for the testing. And similarly, I am splitting these samples in 0.1. It means 9:1 ratio. And next is the random state equal to 42, means how many times I execute my program, my distribution, my output will always be same. So here in this code we are splitting the images into X10 for training, and X train and Y train, and Y train is used for the testing. Similarly, label is being split into this Y train and Y test. It is splitting into Y train and Y test, and images is split into X train and X test. X test will be used for the testing, and its corresponding label is this one, Y test, and X train will be used for the training, and its corresponding label is Y train. Next code is the model building. Basically, for building a AI model for my IDs detection, I have used the keras, and I have imported this keras from the TensorFlow, I have also imported the layers and the models for building by models. And Keras, it is generally a high level API for deep learning in TensorFlow. And layers contains the different neural networks layer that can be used for extracting the features of the images. Next, I have created a model. This is my model. I have created a sequential model, and this line of code will create a sequential model. It means a linear stack of the different layers of the convolution neural network. Then next is this 2D. It is 2D CNN layer, and here I have used 32 filters. It will detect 32 features in the images that are present. And next is kernel size, 3 cross 3 kernel size, and 3 cross 3 kernel size will capture the spatial patterns. That means the visual patterns that are available in the that images, IDG's images. Next is the stride equal to 2. It is used to reduce the size of the incoming feature maps or the image. For example, in the first layer, this much dimension image will pass 128 cross 128 cross 3 image will be passed. Once they passed the exist of this layer, then the size of the image will be reduced by half because I am using this stride value equal to 2. It means this layer will give the output 64 cross 64 comma this 32. And again here in the next layer also I am using this stride value 2. Again here this layer output will generate the reduced size image that will be 32 comma 64, and in each layer the image passes, the size of the image will be reduced by half because I am using the value of the stride equal to 2. Next is the ReLU activation function. Generally it is used for the learning of the non-linearity. Next is the padding equal to same. This keeps the output size the same after applying the filters. Whatever filters we have applied, after applying that filter also, the size of the images will remain the same. Next is the we have used this in our layers, different layers of the convolution neural networks. And here we have used the global average Link 2D. It is we are not using here flatten. We are using the global average Link. It reduces the number of the parameters in our codes and also helps in preventing the overfitting problem. Next, we have used the 128 neurons to process the extracted features that has been extracted from the images. Next is the ReLU activation function. Again, it introduces the non-linearity in our code, and we have set the dropout equal to 0.3. It means it is used to prevent the overfitting by randomly dropping the 30% of the neurons during the training of our model. And finally, at the last layer, we have set the dense value equal to 10. It means there are 10 neurons, and each neurons will be used for each classes. Since our dataset contains 10 different category of eye diseases, so for this we are using 10 number of the neurons at the last layers, and we are using the activation function as softmax. It is a multi-classification problem. If it was a binary classification, we had been using the sigmoid activation functions, but since it is a multi-classification, therefore we are using the softmax activation function here. And since there are 10 different diseases are there, so we are specifying the 10 at a last dense layer. Next, to generate the model summary, we are just writing this code model summary, and it will generate the summary of our models. You can see here, after each convolution layer, the size of the image is reducing because we have set the value of the stride equal to 2, and these are the number of the filters. It will extract the number of the features. This will extract 32 features from the image. This will extract 64 features from the image. This will extract the 128 features from the image. Next is at the last layer we have set the dense layer as 10 due to the 10 different category of the IDJs, and this is the total number of the parameters. So, stands 100,000 lakhs. It is 1,11,050 parameters. This is the size of our models, and all of these parameters will be used for the training. And here till here our model has been designed, has been built. Now we are going to train this model with our preprocessed datasets. And for the training we are using this code here. And for model training we are using the optimizer Adam, because generally the Adam performs better for most of the tasks. So we are using this Adam optimizer with the loading rate 0.0005, and we have used the loss function as sparse categorical cross entropy and matrix as accuracy. And this line of the code is used to train the model. Here our model name is model, so we are training this model using the fit function. We are passing the X train that we have splitted previously, and this is our image. This contains the images of the different 10 category of the IDJs, and their respective label is in this Y train. And we are passing these images in the batch size of 8. It means 8 images will be passed at a time, and next again the 8 images will pass, again the 8 images will be passed. And we have splitted the validation into 0.1. again here also the 90% of the images of this X train will be used for the training, and 10% of the images total will be used for the validation. And we are running our model for the 50 epochs. Now this model, we have trained our model here. You can see during the first epoch our model has only 34% of accuracy. It means it has very low accuracy to recognize the different category of the diseases. But as this epoch increases, this is the second epoch, this is the third epoch, and finally I have run this model, I trained this model till 50 epochs, and at 50 epochs the accuracy of my model reaches to 84%. Since this is for the testing purpose only, I am training my model up to 50 epochs. But if you want a better accuracy, you can train your model for up to 100 epochs also. And similarly, to increase the accuracy you can increase the number of the convolution layer here for a better accuracy. But since it is for the testing purpose, I am only using the 3 convolution layer. But you can increase these convolution layers, and you can also increase this epoch value here. You can also increase your training data sets for the better performance. And once this model is trained, the testing phase begins. And before the testing phase begins, I will save my model for the future references using this line of the code. And once this model is saved, I will load my model using this code, model equal to load model. And once the model is loaded, I will use this model for the prediction to check whether it is performing well or not by using the code model.evaluate. And in evaluate I am passing the x-rays that I have splitted my training sample previously. This is the x-test is the this x-test contains the different category of the images of the different IDJs and their respective labels. And once this model is executed, this line of the code, it is showing I have 81% accuracy. It means it has been able to recognize the different category of the IDJs with 81% accuracy. And similarly, I am predicting my images using this again these samples. Now in this line of the code, I am generating the confusion matrix. Generally, confusion matrix are extremely important because they identify which classes are misclassified. It detects the imbalance in the prediction. Example, if one class dominates, the others are not, and it provides the insights into the model weakness, where our model is performing better or not. And with this code, I have generated the confusion matrix. This is the confusion matrix. This is the true label, and this is the predicted label. I have achieved the 81% of accuracy in predicting, in detecting the a different category of the eye disease. And this line of the code is used to print the training accuracy and the validation accuracy. And you can see here my this blue line represents the training accuracy. See, my accuracy is increasing with every book. These are the books till 50 books. It is increasing. You can see here it has reached up to the something like more than 80% accuracy it has achieved. Similarly, this is the validation accuracy. It is also increasing, and this increasing graph demonstrates the performance of my model is extremely good in detecting the different category of the eye disease. Similarly, I have also used this code for the prediction of my images, and this code is used to randomly display the testing results. This line of the code, and you can see here I entered my testing results. These are the true label and these are the predicted label in the test image. In test image, I have passed this image for testing of my model, how much better my model is performing. Actually, this was disk edema, and model has predicted disk edema. You can see the accuracy here, how much nicely our model has been able to predict the accurate results. It is predicting accurately. Similarly, this eye is of disease myopia, and we have accurately detected it as myopia. Similarly, this disease is diabetic, some kind of disease this, and we have been able to correctly recognize it as diabetic. It was this one, and we have predicted this one. You can see the accuracy of our model in predicting the different categories of the eye disease. Similarly, this test image was of disc edema disease, and we have been able to predict it as disc edema. You can again see here the accuracy of our approach in detecting the different diseases. But here, I think our model is this one. It was healthy. This image is of a healthy eye, but we predicted central serous. But here we were not able to correctly detect, so this is the one mistake is there. And again here, but here we have correctly predicted this was healthy eye, and our model has detected as healthy eye. This is good. And here also it was healthy eye. Again it has predicted healthy eye. This is also good. It was retinal detachment. It was again we predicted retinal detachment. So by seeing these results, we can say that our approach is extremely good in detecting the different category of the eye disease. You can see the accuracy of our models. It is predicting very accurately. Now you can also see here. So this is how you can create a artificial intelligence model in detecting the different category of the eye diseases. Okay, see you in the next topic, in the next session. Till then, bye bye.